All right, so we're starting chapter 7 today, and chapter 7 is going to be a departure for us in terms of the last few days. We've been spending a lot of time doing qualitative chemistry, that is, chemistry without numbers, chemistry with concepts, and that kind of those kinds of ideas. Chapter 7, we're getting back into the quantitative aspects of chemistry, the numbers-based aspects, and we're going to be looking at a concept known as stoichiometry. And stoichiometry, we're really getting into kind of the calculations of chemical reactions. So to do so, we are going to need to have a pretty good discussion here about chemical equations. Now, at this point, we are well beyond the midterm of the course. We are actually closing out week 3 of our summer session, which would be week 9 in a normal semester. And by this point, if we haven't seen chemical equations and know what they mean, we've been missing something. But overall, we're talking about a proportion of reactants and products in a chemical reaction. So we're looking at what happens, what changes on the atomic level. When I go from sulfur trioxide and water as my reactants to making sulfuric acid as a product, something happened in these molecules to allow them to convert themselves into this molecule. And furthermore, if I saw a reaction between iron 3 oxide and sulfuric acid, the reaction I would get there would create water and iron 2, or excuse me, iron 3 sulfate. So we can see that rearrangements are occurring. Things are happening at the atomic level that are allowing these reactions to occur and rearrange themselves accordingly. Now, the other piece of information that I can get from a balanced chemical equation is the physical phase of the reactants. And so the physical phases that we are talking about here are S for solid, L for liquid, G for gas, and AQ for aqueous solution. And remember, aqueous solution means that we have something that is dissolved in water. That's all that aqueous solution means. Now, when we come to balancing equations, we know that the balancing equation is based largely on the general concept of the law of conservation. Now, whether you call it the law of conservation of mass or the law of conservation of matter, for all intents and purposes, they mean the same thing. What we're talking about is the fact that we cannot create or destroy matter in any kind of chemical process. And so when we talk about the law of conservation of matter, what that really means is that every atom that we start with as a reactant comes out in the product in some kind of way. Everything that started here ends up over here. Now, it may not be arranged the same way, but it's going to be present in some kind of form or fashion. And when we talk about the law of conservation of mass, what that means is that the total mass of the reactants has to equal the total mass of the product or products. I can't add or subtract any mass along the way. If I do, that means that I've lost sight of one of my reactants or one of my products. Now, for this class, it probably bears no special circumstance or understanding, but just to review, there is a difference between subscripts and coefficients. Subscripts help us to see ratios of one atom and one element to another in a given compound. So if I have the formula H2O, that means that there are 2 hydrogen atoms for every 1 oxygen atom in that molecule. However, when it comes to balancing equations, what we have to make sure that we recognize is that using subscripts is an absolute no-no. Subscripts are used in terms of determining the overall composition of a compound. If I change those subscripts, I change the composition of that compound. And that means that the compound will have different kinds of meaning, different kinds of reactivity. So we're not going to do that. If we need to balance a chemical equation, we're going to use coefficients to do that. And so that's the important thing to kind of remember and look at in the balancing of equations, is that we use coefficients to help us balance equations, not subscripts. Because if we change the subscripts, we change the meaning and the identity of the atom. And the classic example I like to give is if I have iron with a coefficient of 3 in front, that means that I've got 3 iron atoms just hanging out in the same relative space. There's my 3 irons. If I have Fe3, changing it up, what that means is that I've got my 3 iron atoms. They're somehow connected to each other through covalent bonding. We've got some kind of molecule here. And they're sharing electrons in a covalent way, or some kind of weird ionic structure. Or maybe we've got a ring structure or something like that. Who knows? At any rate, this molecule is going to behave much differently than these atoms will. And so it's important that when we are balancing equations, we really get our structures right. We really get our understanding set up well. Now, if you've been doing chemistry for a while and you already know how to balance equations, then this is probably going to be redundant for you. You probably have your own methods and your own ways of doing things. If this is something that you struggle with, what I would encourage you to use is something called the atom economy method. Now, the atom economy method is slow. It is deliberate. It makes sure that every single atom in the equation is accounted for. So basically how it works is you take an equation and you split it in half. Reactants on the one side, products on the other side. And you look at each side and you say, okay, on this side of the equation, on my reactant or on my product side, I've got this much stuff. And on this side of the equation, on my reactant side, I have this much stuff. And I start playing around with the coefficients, changing my counting of everything until I get everything evened out. And when I get everything evened out, then I know, okay, the equation's balanced. But it's deliberate. It's kind of slow. If you're just starting out, it's a good way to start because it makes sure that you get everything right. But if it's not that way for you, if you've already been doing this for a long time, then you're probably going to end up going and doing balancing by another method called inspection. And inspection is a lot easier, where you just go, okay, I kind of recognize the pattern here. The pattern tells me, okay, I need a 2 over here, I need a 3 over here, and I can very quickly evaluate whether or not I've balanced it. That kind of work just takes time to do. It's a matter of practice. And so as you're kind of looking ahead to some of the activities that are due or are soon to be due, you'll see in there, there's a balancing equations post-lecture that walks you not only through the atom economy method and some of the tips and tricks, but also how to recognize certain types of equations by type. And if you can recognize, hey, I've got a double replacement reaction here, that actually helps a lot in terms of telling you the kinds of reactions, the way the pattern kind of falls in terms of what the reaction is and how to balance it. So inside of the atom economy method here, there are some things that you can do that'll make it easier for you to um, follow this along. And it's rather simple, actually. First of all, hydrogen and oxygen in this type of chemistry tend to be very common elements. You tend to find hydrogens and oxygens in lots of things, oxygens especially. And so the first tip is this: leave those till the end. Chances are, once you've balanced everything else, hydrogen and oxygen tend to kind of take care of themselves. And or if they don't take care of themselves entirely, it becomes really easy to see how to take care of it. The second thing, especially if we're dealing with replacement reactions, either single replacement or double replacement, clustering is a really good idea. And what I mean by that is, at this point in time, we've seen the polyatomic ions. You have had to balance and recognize and name and do all sorts of things with polyatomic ions. So you've got all of that at your disposal. Now it's a matter of recognition. You can recognize, okay, hey, that's a nitrate right there, NO3. Hey, there's nitrates on both sides of the equation. Instead of tracking nitrogen and oxygen individually, why don't I track nitrate ions as I go from reactant to product? If I can track the nitrate ions, I can go, okay, there's 3 of them over here, there's 1 of them over there. I'm going to triple the one that has the nitrate in it in the product. That'll work. So let's take a look at some examples then. So I've got an iron oxide compound. This is actually a combination of iron 2 and iron 3 in this iron oxide compound. And it is reacting with hydrogen to make iron and water. So the first thing I'm going to do, draw a line right down the middle. That's going to split my reactants and my products. And on the reactant side, I can see that I have I have 3 irons. I have 4 oxygens, and I have 2 hydrogens. On the product side, I have 1 iron, 1 oxygen, and 2 hydrogens. Now, if I'm following this through and using the methodology that I just laid out, my first thought, my first instinct is going to be to get rid of the imbalance in the irons. And to do so, I would need 3 of these irons here. And that would turn this 1 into a 3. Now, the other thing that I can look at, this is an unpublished tip, but it's a good one nonetheless. If I see that I have a compound that has multiple subscripts in it, those subscripts are usually going to end up as coefficients on the other side of the equation. And if not as subscripts, they're going to help to lead us to the correct subscripts. So 3 from the iron here becomes 3 irons there. 4 on the oxygen there is going to become 4 waters. And so that turns my oxygen 1 times, or 4 times 1 gives me 4. That also changes my hydrogen. 4 times 2 gives me 8. And so I've got my irons balanced. I've got my oxygens balanced. The only thing I don't have balanced now is the hydrogen. And if I put a 4 here, 4 times 2 would give me 8 for the hydrogen now. 3 irons, 4 oxygens, 8 hydrogens. I've got me a balanced equation. Right. Any questions so far?
No.
All right. All right, let's take a look at another example. Here I've got butane, C4H10, reacting with oxygen to make carbon dioxide and water. Now, these types of reactions, combustion reactions, are by far the more tricky to balance usually because we've got multiple elements, we've got oxygen in a bunch of different places. These can be just kind of generally tricky overall because there's no way to really shrink them down. But starting with carbon, I have 4 carbons, 10 hydrogens, 2 oxygens. And on the product side, I have 1 carbon, 2 hydrogens, and 2 plus 1, 3 oxygens. And so again, this is where things are a little bit more confusing because unlike in the previous ones, we've got oxygen in multiple places. So it's gonna be a little bit tougher to balance. But if I start here at the top, and again, I start with my coefficient or my subscripts here in the C4H10, I bring them over. So 4 for the carbon dioxide, 10 hydrogens means I'm going to have 5 waters to balance those out. Now, if I do all of this math now, 4 times 1 is 4 carbons. 5 times 2 is 10 hydrogens. And 4 times 2 is 8 for the carbon. 5 times 1 is 5 for the other oxygen here. 8 plus 5 now gives me 13 oxygens. So I've got the carbons balanced. I've got the hydrogens balanced. To balance the oxygen, well, hold on a second. I need 13 oxygens, but I only have pairs of oxygens over here. How exactly can I get 13 if I have to count by twos? Yep, that's exactly right. There's 2 ways to go about it. We can't do anything, or we have to cheat it. And cheating it would involve either putting in a number here that is not a whole number. 6.5 times 2 is 13. Or I could put in a fraction in that spot. Fractional form of 6.5 is 13 halves. But any way that you look at this, you'd go, oh, that doesn't really make any sense. From a molecular standpoint, how do I get half of a molecule? And the reality is, you're correct. You can't get half of a molecule. But what you can do is, if we take into consideration that this is an equation, this is basically a math problem, how do I get rid of fractions? Well, I multiply by whatever's in their denominator. So if I multiply this whole thing by 2, that would give me 2 butanes. Knock out my eraser here. 13 halves times 2 would be 13 oxygens. 4 times 2 would be 8 carbon dioxide. And 5 times 2 would be 10 waters. So if I did that multiplying by 2, now let's reevaluate. 2 times 4 is 8. 2 times 10 is 20. 13 times 2 is 26. 8 times 1 is 8 for the carbon. 10 times 2 is 20 for the hydrogen. 8 times 2 is now 16 plus 10. So my grand total here is 26 for the oxygen, and I can look across 8 carbons, 20 hydrogens, 26 oxygens. I've got a balanced chemical equation now. So, like I said, this is probably the more complicated kind of problem that you can get. I'm not going to say it's as complicated as it gets, because that's certainly not true. But in terms of ones that you can balance just by looking at them and following this kind of methodology, this is about as complicated as it gets. Any questions about this example?
I don't have any.
Okay, let's move on. Okay, I've got another example here. I've got potassium sulfate reacting with barium chloride to make potassium chloride and barium sulfate. Now, here is an example of the other type of trick I was talking to you about. In this example, I can see I've got sulfate, SO4, present on both sides of this equation. So instead of tracking sulfur and oxygen individually, which in many cases, not in this one, but in many cases could get a little bit sticky, I'm going to evaluate it all together. So I have 2 potassiums. I have 1 sulfate. I have 1 barium. And I have 2 chlorides. And on the opposite side, I have 1 potassium, 1 sulfate, 1 barium, and 1 chloride. Now, this type of reaction is called a replacement reaction. And the reason it's called a replacement reaction is we can see that, basically speaking, the potassium and the barium have switched spots. Potassium goes from being with sulfate to being with chloride. Barium goes from being with chloride to being with sulfate. They switch places. Replacement reactions are usually pretty easy to balance because they tend to cluster together a little bit, And it's usually pretty easy to see, especially if you write it out. It's usually pretty easy to see where things are balanced and where they are not balanced. So I can look at this already and say, look, my barium and my sulfate are already balanced. The only thing that's not balanced are my potassium and my chlorides. And that's easily fixed. If I put a 2 here, I now have my 2 potassiums, my 2 chlorides. Everything's now balanced out. Right? Any questions about this example?
No.
All right. So what I want you to do then is take a couple of minutes, go ahead and copy these down, and try to balance these two equations on your own. They're both combustion reactions, so they're on the tougher side. Go ahead and try to balance these, um, and um, and come up with the correct answers for what the coefficients should be, um, in doing them. Once you have some answers of your own, feel free to share with each other and see if you guys are on the right track.
Okay. Hold on with the O. $24 for the O on the left side, but I could be wrong.
Yeah.
I have to do the right, match the right side up.
I'll put it in here. We'll see where it goes. Okay. What about the carbon dioxide?
That'd be 16 multiplied by.
Okay. And then the water.
It'll be, I think that's where I messed up. And wait, let me see. No, I got 16.
All right, 16 for carbon dioxide. What about water? 16 also?
Yeah, but I could be wrong with my numbers. Yeah, I mean, because I'm trying to put, from the right side, the O is supposed to be a total of 48.
Okay, so I think this is where we're running into problems. Let's clear this and come back to that later. Okay, so if I double the octane, if I double C8H18, 2 times 8 would mean I need 16 carbon dioxides because I need 16 carbons, right?
Mm-hmm.
2 times 18 would mean I need 36 hydrogens, which would mean I would need 18 waters. 18 times 2 gives me 36.
I calculated wrong
Okay.
because
Now
I
for
got 32. So yeah, no. Okay, I'm hearing what you're saying.
so now if I put those two together, 16 times 2 is 32 plus 18, that's 50 for my oxygen.
My calculation was off. I don't know. I had put 32, but okay, I messed up there. So I didn't get 36. I did it wrong. I did it wrong. So no, just erase it because I put 32 down. I multiplied wrong.
So this would be the balanced equation for number 1. 2 butane plus 25 oxygen makes 16 carbon dioxide and 18 waters.
Okay.
Now for the second one we're going to have to do, again, a similar kind of process. Now, this one is also a combustion reaction. It's also going to have a little bit of trickiness to it because of that. If I just start by kind of writing out what I have 1 nitrogen, I have 3 hydrogen, I have 2 oxygen, and on the opposite side, I've got 1 nitrogen, 2 hydrogen, and for the oxygen, I've got another one of those sticky oxygen in multiple places, 3 in total. So my first instinct would be to look at this and go, okay, nitrogen is completely balanced. Let's not touch it. And that leaves hydrogen and oxygen. Now, hydrogen is only in 1 molecule each. It's in water on the product side. It's in the ammonia on the reactant side. That's going to be the easier of the two to balance. To balance it, I'm going to need a lowest common multiple between 2 and 3. Lowest common multiple between 2 and 3 is 6. So I need to get 6 hydrogens, which means I'm going to need to triple the water and double the ammonia. Now, doing so has put my nitrogens out of balance. I now have 2 nitrogens on the reactant side and only 1 on the product side. So I'm going to need to double the nitrogen dioxide. And so if I do that, my oxygens I need to recalculate. I now have 4 oxygen from nitrogen dioxide and 3 from water for a total of 7. And I run into the exact same problem that I would have run into up here, and that is, how do I get 7 when all the oxygens come in pairs? And so the solution to that problem is exactly the same as before. I have a fractional coefficient, 7/2, which doesn't really make a whole lot of sense. So I have to double everything. And if I double everything, then that leaves us with 4 ammonia plus 7 oxygen, making 4 nitrogen dioxide and 6 water. And if we follow everything through, just doing our calculations again, that now gives me 4 nitrogens, 12 hydrogens, and 14 oxygens on the reactant side, 4 nitrogens, 12 hydrogens, and 8 plus 6 for 14 oxygens. So 4 nitrogen, 12 hydrogen, 14 oxygen. Our equation's now balanced. So, as I said, these reactions are probably the toughest on their own to sit and balance. They require the most practice to do, and it's not uncommon that we have to kind of cheat in a fraction and then multiply by 2 to get it to work, especially in the case where with these combustion reactions. But that's ultimately what we have to do. Any questions about equation balancing? All right, hearing no questions then, let's take a 10-minute break, and then we'll talk about stoichiometry, and that'll close us out for today. So it is 10:05 at the moment. Come back at 10:15, and we will resume our discussions with stoichiometry. All right, so in this part now, we're talking about stoichiometry. And with stoichiometry, we're really moving into the quantitative aspect. And so stoichiometry is based upon the law of conservation of mass. Law of conservation of mass says that the sum of the masses on the reactant side has to equal the sum of the masses on the product side. And all that stoichiometry is just this quantitative relationship between those masses, and using our understandings of moles and balanced chemical equations and grams and particles, and kind of bringing together those two worlds. So we had our calculations in chapter 2, where we were able to go between masses and moles of compounds and particles and do all those kinds of interconversions using molar masses or Avogadro's number or that kind of stuff. And here in chapter 7, we're doing the same thing, only we're integrating one extra aspect, and that one extra aspect is the balanced chemical equation. And so using the balanced chemical equation, now we are able to go not just looking at how many grams of carbon dioxide do I have if I have this number of moles, but if I have carbon dioxide reacting with iron in this reaction, how much product can I get? And so we're taking our understandings, we're expanding them a little bit, and making them a little bit more useful to us in a practical sense. Now, in order to do calculations of stoichiometry, we have to know some things. And of the things that we need to know, these last two things, as I mentioned before, we've already discovered. We've already discussed molar masses of reactants, molar masses of product. We did that in chapter 2. The only thing we haven't introduced is this idea of the mole ratio. But if you understand the concept of the balanced chemical equation, then the mole ratio is just given to us by that balanced chemical equation. And so stoichiometry can actually be visualized and organized as a series of calculations very similar to what we saw in chapter 2, but with an additional wrinkle. And so if you want to look at a way of organizing your stoichiometry, I would come back to this map concept that we explored in chapter 2. Now, in chapter 2, we had this particular concept, and instead of tying together moles of different substances, we looked at converting moles of a compound into moles of an element, moles of an element into particles of an element, or mass of an element using the chemical formula. Well, this is really not all that different from that. Instead of going from moles of carbon dioxide to moles of carbon, like we would have in chapter 2, we're going from moles of carbon dioxide to moles of water. And the way that we tie the two together is with that balanced chemical equation. Otherwise, the calculations are exactly the same as what we saw in chapter 2. Particles and moles are tied together by Avogadro's number. Grams and moles are tied together by molar mass. And so this mole map is a way for us to organize our calculations so as to set up our dimensional analysis, our conversions, to get us from one of these boxes to another. And so what we're going to see is that all that we're really going to be asked to do is, let's say that we start with grams of one substance and we want to convert that to grams of another substance. Well, that's actually not that difficult, because all I have to do is follow the map, turn the grams into moles of the first substance, turn the moles of the first substance into moles of the second substance, and then turn the moles of the second substance into grams of that substance. And if I follow the logic here, 1, 2, 3 arrows means I'm going to have to do 3 conversions, 3 bars in that dimensional analysis to make that conversion possible. And that's really all that stoichiometry is just an extension of dimensional analysis to talk about reactions and the quantitative nature of those reactions. So let's take a look at an example. In this example, I've got 13.33 grams of aluminum burning in excess oxygen. The question is, what is the mass of aluminum oxide that is formed as a result of this reaction? Now, before I can do any of this stuff here, I need to get into my brain. I need to look at what is the balanced equation that we're looking at. I've got aluminum reacting with oxygen to make aluminum oxide. And so from a balancing standpoint, we'll just do this by inspection. I've got a lowest common multiple issue to deal with here. So I'm going to need 3 oxygens and 2 aluminum oxides to make the oxygens at 6 each. That means I'm going to have 4 aluminums. So there's my balanced chemical equation. 4 aluminum plus 3 oxygen makes 2 aluminum oxides. Now that I have this balanced equation, now I can look at, okay, here's what my mole map looks like. Okay, let's try it that way. So now that I've got my balanced chemical equation, now I can look at my mole map and say, okay, I have a mass of aluminum. That mass, we were told, was 13.33 grams. Now I need to convert that mass of aluminum into moles, the moles of aluminum into moles of aluminum oxide, and then the moles of aluminum oxide into the mass. And if I follow this step by step, the logic kind of takes care of itself. My first step is going to be to convert the mass of aluminum into moles. The second step is going to be converting the moles of aluminum into moles of aluminum oxide. The third step is going to be converting the moles of aluminum oxide into grams. Just as a word of caution for us, every calculation step should be done at the same time. We should not be rounding in between our calculation steps because additional rounding can create and compound errors, which could impact the accuracy of our final result. So I've got my 13.33 grams of aluminum. My first step is to convert that grams of aluminum into moles of aluminum. Now, where would I get that information to make this conversion?
For the periodic table.
Yes, thank you. So this is where the periodic table is going to come in. 1 mole of aluminum for aluminum's molar mass 26.98 grams. So that step is going to eliminate our grams of aluminum. We've now got moles of aluminum. My second step is going to be taking moles of aluminum and converting it into moles of aluminum oxide. Now, this information comes from the balanced chemical equation. It actually comes from the coefficients in that balanced chemical equation. So I know I need 4 moles of aluminum for every 2 moles of aluminum oxide. Now, as a word of caution here, it might be tempting to you to try to reduce this in your head and say, okay, well, it's really a 1 to 2. 1 aluminum oxide for every 2 aluminums. I can get that just from the chemical formula after all. I would caution you against this because it's easy to make mistakes that way. And if the substance is in multiple compounds, it may not be as cut and dried. So even though it looks kind of silly to make a fraction here that is essentially 2/4 instead of 1/2, go ahead and use it because the coefficients will never steer you wrong. And even though your calculator knows that 2 out of 4 is the same as 1 out of 2, it's not going to care so long as you put in the coefficients correctly. Anyway, moles of aluminum have now canceled. I have moles of aluminum oxide. Last step, I need to convert that moles of aluminum oxide into grams of aluminum oxide. Once again, we're going to need the periodic table for that. And for aluminum, 26.98 times 2 for the 2 aluminums. For oxygen, 16.00 times 3, because there are 3 of those. I get 101.96 grams of aluminum oxide for every mole of aluminum oxide. And so my moles of aluminum oxide cancel. I'm left with just the grams. Now to solve out everything, all of my units have canceled other than the grams. 13.33 multiplied by 2 multiplied by 101.96 divided by 26.98 and divided by 4 to, how many significant figures should I use here?
Two.
Four.
It should be 4. Why 4?
Because you're dividing.
Yeah, we're multiplying and dividing here. So we need to round based on the number, the measurement that has the fewest sig figs. And so I have 4 significant figures in this. I have 4 in that. These numbers are exact. I have 5 in this mass. So of the sig figs that I can count, 4 or 5, 4 is the lower number. So I'm going to round to 4 significant figures. That's going to give me 25.19 grams of aluminum oxide. All right, any questions? All right, hearing none, let's look at a second example. how much carbon dioxide enters the atmosphere each year from the combustion of 6.8 times 10 to the 12th kilograms of carbon. So this particular problem is of significant interest here in Indiana, since most of our electricity comes through the combustion of coal, which is primarily carbon. Um, so how much carbon dioxide is being put into the atmosphere from carbon burning, from coal? Now, to answer this question, again, we're going to need to have a balanced chemical equation. This one's a good bit easier than some of the other ones that we've been dealing with. I've got carbon reacting with oxygen to make carbon dioxide. And so I don't need to do an atom economy or anything. I can just look at this and go, okay, I've got one carbon on each side. I've got two oxygens on each side. This is already balanced. But if we follow along in terms of our map, we understand that we have a starting amount of carbon, and we're going to eventually turn it into carbon dioxide. So the process we're going to undergo is very similar to the previous problem. 6.8 times 10 to the 12th kilograms of carbon. Now, our approach from here can take a number of different twists and turns. Since our molar masses are in grams, one common conversion would be to take this kilogram and turn it into grams first. So 1,000 grams in a kilogram. That way I can get rid of my kilograms. Now with that in mind, I want to turn grams of carbon into moles of carbon. For that, I would need my periodic table. Molar mass of carbon is 12.01. 12.01 grams of carbon in 1 mole of carbon. So my grams of carbon have canceled out. I now have moles of carbon. And so I need to turn my moles of carbon into moles of carbon dioxide. Once again, I need my balanced chemical equation. Balanced chemical equation says that each of those is a 1. 1 mole of carbon for 1 mole of carbon dioxide. My moles of carbon cancel. Last step, turn my moles of carbon dioxide into grams of carbon dioxide. Need the periodic table again for that. Carbon is 12.01. Each oxygen is 16.00. So molar mass here, 44.01 grams of carbon for every mole of carbon dioxide. My moles of carbon dioxide cancel. So if I put this into the calculator, 6.8 times 10 to the 12th multiplied by 1,000 multiplied by 44.01 divided by 12.01. I get how many significant figures here?
I want 4. I want to say 2, but it's
This time it is 2.
okay. The 6.8, so I was right. Okay. That's
Yeah, the
fine.
6.8 only has 2, so you only have 2 here. So
Okay.
2.5 times 10 to the 16th grams of carbon dioxide. That is our mass of carbon dioxide. Now, if we wanted to turn this into kilograms again, we would divide by, we could divide by 1,000. It would be 2.5 times 10 to the 13th kilograms. But that's all depending upon what they ask us for. They just ask us for an amount here. Grams is an amount, unless otherwise specified. All right, any questions about this one?
No. Mm.
All right, try this one yourselves. In 2014, power plants in the United States, these are natural gas power plants, consume 2.2 times 10 to the 11th kilograms of natural gas. How many kilograms of carbon dioxide were released into the atmosphere from these power plants? Now, we've already given you the balanced chemical equation. You just need to do the stoichiometry. So I'll give you a couple of minutes. Go ahead and organize the calculations. And there's only 2 of you in here now. Just let me know when you're finished and we'll go over it.
Okay. You want to know the step?
Okay, so let's just walk through it, and if you get something different from what I'm about to show, then stop me and we'll talk about it.
Okay.
Okay, now we could follow the same process that we did in the previous problem, but there is one little shortcut I'm gonna show off to you right here. Since we're keeping everything in kilo units the whole way through, rather than multiplying by 1,000 and then dividing by 1,000 at the end, if we understand that the relationships that we're talking about all would exist in kilo units above and below, we can actually simplify this problem a little bit. And what I mean by that is our first step would be the conversion from mass of methane to moles of methane. Well, if I, just for the sake of argument here, kept everything in kilo units, the ratio would be the same in terms of 1 kilomole would be equal to the molar mass of methane in kilograms. So 12.01 plus 4 times 1.01, 16.05. And so that would get rid of our kilograms there. My second step would be the molar step. Kilomoles of methane to kilomoles of carbon dioxide. And the relationship here is 1 to 1. And then finally, kilomoles of carbon dioxide to kilograms of carbon dioxide. And as we saw in the previous problem, molar mass of carbon dioxide, 44.01. So your process probably looked very similar to this. If you converted the kilograms to grams, and at the end of this step turned the grams back into kilograms, you would have found that you multiplied by 1,000 in this step and then divided by the same 1,000 in a later step. All that this did was essentially remove those two steps that would have canceled out anyway. But if I do this, 2.2 times 10 to the 11th, multiply by 44.01, divided by 16.05 to two significant figures, I get 6.0 times 10 to the 11th kilograms of carbon dioxide. Does that line up with what you found? Maybe different process, but same function, same answer.
Yeah.
I got to the 14th, but I forgot. Well, I didn't know. Well, I forgot about the 1,000.
Yeah, that step right there. So the 14th would have been grams. Since the problem specifically asks us for kilograms,
Mm-hmm.
we would have had to divide that number by 1,000.
Okay.
To turn the grams into kilograms. All right. Any other questions?
No.
All right. One last concept to discuss for today, and that is the concept of yield. So now that we can evaluate what should happen in a chemical reaction, we can compare that to what did happen when we do the experiment ourselves. And so the theoretical yield, that is the yield that is predicted by stoichiometry. And so that tells us how much we should have gotten. Our experimental yield, so let's say that we did that reaction exactly in a laboratory, which I don't know how we would, but let's leave it at that. Let's say that we did it in small scale, and instead of burning, what was it, 2.2 times 10 to the 11th kilograms, let's just say that we burned 2.2 kilograms. We had burned 2.2 kilograms in our laboratory and then measured how much carbon dioxide was produced from that 2.2 kilograms. We could, that amount that we got in the laboratory would be our actual yield. Now, generally speaking, actual yield is less than theoretical yield. And the reason for that is that actual yield, when you actually do an experiment, there are often side reactions, there are often impurities that you have to deal with. So there's a lot of other factors that come into play. And generally speaking, your actual yield suffers as a result of those other things. Now, how well your production process is, how well it goes, it can be measured by something called percent yield. Now, percent yield is just a ratio. It is telling us the blend between the actual yield, what you got in your experiment, compared to the theoretical yield. So actual over theoretical multiplied by 100% is our percent yield. Now, there's another version of this that is often used in physics or in engineering fields called efficiency. And efficiency has the same kind of idea. It is the actual yield divided by the theoretical yield. The only difference there is the lack of multiplying. So if I just had those two numbers in the ratio and I just divided them, that efficiency rating would be given as such. It would be a decimal number between 0 and 1. Closer to 1 it is, the more efficient the process is. Now in engineering and physics, Usually the yields that they're talking about are energy as opposed to matter. Um, but the idea and the process is essentially the same um, in terms of what it is that you're calculating and comparing to each other. So I just wanted to kind of throw that one out there as just a possibility. Let's take a look at an example and then we'll call it a day. Let's look at the production of ammonia, nitrogen reacting with hydrogen to make ammonia. If I have 18.2 kilograms of ammonia with a molar mass of 17.03 grams per mole, and it comes from a reaction mixture that initially contains 6 kilograms of hydrogen and excess nitrogen, meaning all of the hydrogen is going to react, what is the percent yield of the reaction? Okay, very similar process to the one that you just did. I can start with my 6 kilograms of hydrogen, and since we're staying in kilos the whole way through, we can use kilo conversions just the same way that we were using base unit conversions. So for hydrogen, it was 2.016 kilograms of hydrogen for 1 kilomole of hydrogen. That gets our kilograms of hydrogen to cancel out. Our next step is 1 kilomole of hydrogen for, or excuse me, not 1 kilomole. Gotta use our balanced equation here. 3 kilomoles of hydrogen for every 2 kilomoles of ammonia. And so our kilomoles of hydrogen cancel. And then finally, the last step, every kilomole of ammonia is going to have a mass of 17.03 kilograms. And so my kilomoles of ammonia cancel. And I end up with just kilograms of ammonia. So if I do the calculation, 6 times 2 times 17.03 divided by 2.016 divided by 3 to 3 significant figures, because that's what I started with here with the 6 grams of hydrogen. 3 significant figures, I got 50.7 kilograms of ammonia. Now this, since it was done via stoichiometry, this is our theoretical yield. To calculate the percent yield, I need to take this yield divided by, this is what we actually got, times 100%. So percent yield is equal to my actual yield, 18.2 kilograms, divided by my theoretical yield, 50.7. Then multiplied by 100%. And so if I do that calculation, 18.2 divided by 50.7 times 100, I get 35.9%. And for this particular reaction, that's actually about right. Unless we work under very specific pressure circumstances with the production of ammonia, the ammonia production is actually very poor. We usually have to get it into some pretty high pressure situations to get the ammonia yield to be much more efficient, much higher. Any questions about this example?
No.